Okay, so my name's Bart Baddeley, and I'm a freelance data consultant with a sort of specialisation in machine learning. A little bit of background, I was in academia for a long time. I did a PhD in neural network modelling. Then I spent 5 years modelling ant navigation. And in the last 2 years, I've been working in the data science area. So I'm a sort of scientist who's turned into a data scientist. I'm going to talk to you about data clustering. I'm going to start by just sort of pointing out that all of this IPython notebook information is in this IPython notebook, which can be downloaded at GitHub. There's quite a lot of code that I'm going to go through, and I'm not going to actually stop on the code. I'm going to whiz through it quite quickly. But if you're interested in sort of a better understanding of what's really going on, have a look at the repo. So to start off with, just quickly sort of summarize what I'm going to talk about. I'm going to start off by just sort of motivating why you want to cluster data. Then I'm going to introduce k-means clustering, which is an algorithm that I'm sure many of you have come across before. Continue with some tips on how to use k-means clustering and when it's appropriate, when it's not. Then provide some insight into how you make decisions about which of your clustering solutions are good, and deciding on things like the number of clusters you should try and find. And then I'm going to finish up with a discussion or a description, explanation of spectral clustering, which is another widely used clustering algorithm. So, to start off with, why would we want to cluster data? There are two main reasons that you'd want to cluster data. The first is as a sort of pre-processing stage to another data analysis. And the second is actually just as an exploratory data analysis technique in its own right. There are a large number of application domains. Just to name a few: data summarization, recommendation systems like collaborative filtering. You can use it for customer segmentation or for segmenting other sorts of objects into coherent groups. Document clustering. It's used a lot in biological data analysis for clustering gene networks and for things like analyzing social networks and networks in general. So it's clearly a key tool for a data analyst, and whilst there are many tools out there that provide you things like scikit-learn, which are fantastic, I think it's useful to actually understand a little bit about what's going on behind the scenes, so that if things don't work out quite how you want them to, then you stand at least some chance of working out why things aren't working out. It's a slightly weird sentence. So, k-means clustering. I guess any of you that have looked at clustering data will have... Oh, no. Sorry, I'm going to have to run the code. It's all... Sorry. No, not that one. Cell menu. Cell? Ah. Run all. Does that just go through the whole thing? And okay. Ooh. That's not looking nice. Okay. Sorry about this. Okay. So k-means clustering. As I said, I'm sort of using some of the code from the scikit-learn to run k-means clustering and things, but a lot of the code I'm sort of writing myself. Have a look at it in your own time. So k-means clustering. Anyone that hasn't come across it, it's a very simple algorithm. It's very easy to understand. It's very easy to implement, and it works pretty well in a lot of instances. So the basic idea is that it's an iterative algorithm. You start off by deciding how many clusters you want to look for. You initialize your cluster centers either randomly or some other way, a little bit more involved. And then you just step through a two-step iterative process where you assign each data point to the nearest cluster center, and then when you've assigned all of the data points, you update the cluster center to be the mean of the data points that have been allocated to it. This is a convex optimization problem, so it means that you will always find a solution. However, you're not guaranteed that this is going to be the globally best solution. So I guess that's the first thing that you should know about clustering algorithms, is that you don't necessarily end up at the best solution. And so for k-means clustering, the standard thing is to run it multiple times and pick out the best solution that you come up with. I'll come on to what the best means in the context of k-means clustering in a minute. So just to show you that it works, we've got this very obviously clustered data set, and this shows the output of running k-means clustering on that particular data set. What you're seeing, although it's almost impossible to distinguish, is the cluster center of the process that was used to generate the data, and the k-means clustering center having run it to a point where we decided that we're happy with the solution. In this instance, there's just two data points that are wrongly classified, and we know they're wrongly classified because we've set up this artificial data, but actually they look like they probably belong in those, the clusters that they've been assigned to anyway. So, when's it useful and when's it not going to work so well? So the first instance that it might not work so well is if our clusters come from data that has different scales and different dimensions. So here we've got a similar sort of clustering problem. To the human observer, it's obvious that there are three clusters there. However, if we run k-means clustering on this data set, we end up with this solution, which is clearly suboptimal. And that's because k-means clustering implicitly assumes that your data is well described by a centroid and is of the same scale in every dimension. So, number 2 take-home message. Make sure that you understand that your data is scaled to a reasonable extent. It's the same scale in the different dimensions that you're using. So what happens if we add in more dimensions? So try to visualize 3 dimensions. So in this instance, I've just added in a third dimension. Let me just make sure yeah. So I've added in a third dimension that contains no information. So the third dimension has the same mean and variance for all 3 clusters. And we can see that the original 2 dimensions that we played around with before, we've got nice separation and obvious clusters. If we plot the first and the third dimension, we see that there's an overlap, and the second and the third, we again see that this third dimension contains no useful information. Is this going to be a problem? Is it going to disrupt our clustering algorithm? And the answer in this case is to a large extent no. So despite this added dimension that contains no information, we're still finding a useful cluster. We can carry on adding in more irrelevant dimensions and still end up with reasonably good performance. So in this case, I've increased the dimensionality to 9 or 10 dimensions. And for each of these dimensions, I've kept each of the clusters have the same mean and variance. So just adding in dimensions that have no information that would help split the data into clusters. Because I know that the 2 dimensions that actually hold the useful information are the first 2, I can still plot those 2 dimensions and see what the clustering results look like. So in this instance, we've added in 7 new dimensions, and it hasn't really affected things. Things are still working okay. We've got a sort of a handful of data points that are on the edges that are starting to get wrongly classified, but we're still doing okay. So what happens if we have a large amount of variance in just one of the single dimensions that we've added? So in this case, we've gone back to 3 dimensions. We've got the original nicely well separated 2 dimensions that we've been playing around with, and shown the other plots of the second versus the third and the first versus the third. And we see that this new added dimension has a different scale. And just sort of going back to what we were saying before, we know that if we have different scales and different dimensions, it can cause problems. So in this instance, when we run the k-means clustering, it goes horribly wrong. And we just end up with a bit of a mess. So sorry, I'm just, okay. So play the same sort of game, but we just add noise into this third dimension, and we get the same problem. So noise is rather than having it a Gaussian spread, it's just a random spread over the same sort of range. And again, it can disrupt the clustering. So what does this tell us? It tells us that we should be careful when adding in new dimensions to our clustering, because every new dimension that you add in, if you're not sure that it's actually providing information, you're also running the risk of introducing one of these things that will break the algorithm. There's another point that is worth knowing about, which is in high dimensions, you run the risk of one of the features of the curse of dimensionality, which is that as your dimensionality of your problem gets larger and larger, the notion of similarity actually starts to break down. So the difference between, if you measure the Euclidean distance between an arbitrary point and its nearest point and its furthest point, that difference will get less and less and less and less as you add more dimensions, till the point at which the similarity of all points to all other points becomes dominated by noise, and basically the notion of similarity in high dimensions actually starts to break down. So if you run your clustering algorithms in very high dimensions, expect to get nonsense out. And you will, one of the things you will always get a result out of a clustering algorithm, and it's down to you as a practitioner to work out whether that actually means anything. So, one other thing that I should explain about k-means clustering before I move on to talk about some other aspects of the clustering approaches that I'm talking about. K-means clustering, as I said earlier, makes this assumption that your data is well described by a centroid and an area around it. So if we've got data that looks like this, and as human beings we can see that there are 2 obvious clusters, k-means clustering is not going to work well in this instance. If we run the k-means clustering on this particular data set, what we end up with is this. And clearly that's not what we're after. So another thing to bear in mind when you're thinking about using k-means clustering is have an idea of what you think your data will look like. If you think it's well described by sort of point clouds, then maybe k-means clustering will be okay. If it's going to be looking more like this, be very wary. So, moving on to trying to decide between different results. So I said at the start, it's usual to run k-means clustering multiple times and pick the best result. But I wasn't clear about what the best result was. So for k-means clustering, there's actually a very nice and easy metric that we can use. So if we set up an example where we know that there's one clustering is working better than the other, so we've run k-means clustering on 2 data sets, and we've kind of hobbled one of them, given it a nasty starting point so that it's making some errors. And the other one we're doing correctly, and so it's getting a nice result. Because we've set up this artificial experiment, we can actually plot exactly the number of wrong and correct labels for our clusters. So how can we automatically work out which of these 2 clustering results we should be using? And for k-means clustering, the final error in your clustering, which is sometimes referred to as the inertia, gives a nice, easy way to determine. So if we plot the inertia, which is basically the sum squared error between each of the data points and its nearest center across the whole data set, for these two runs, we see that the first run, which we know was the better one, shows a smaller inertia score, and therefore that should be the one that we'd pick. So moving on to choosing the number of clusters that you look for, you might naively think that you can use the inertia, so look for the sum squared error. Actually, it turns out that that's not the right thing to do, because as you add in more clusters, your sum squared error is going to get lower and lower and lower. So it doesn't provide a useful metric for actually making decisions about how many clusters you think should be in your solution. So what else can you use? There's a number of different metrics that all work to some extent. Some are better than others. The one that I found the most useful and also in a way the easiest to understand is the silhouette score. And the silhouette score, or the silhouette coefficient, basically measures the nearness of all the points within your own cluster and compares it to the distance between the data point and all the data points in the other clusters. So it calculates a ratio between those two values. So one of them is the compactness of the cluster that you're part of, and the second is your overall distance to the other data points that are not part of your cluster. Hopefully that will become a little bit clearer. It may be a little bit garbled the way I explain that. But if we look at the previous experiment and we measure the silhouette coefficient, we can see that the true number of clusters is 3, and the silhouette coefficient correctly flags that up as being the best solution. So just to summarize so far, k-means clustering is good if our data is well described by centroids. Be careful if data has different scales in different dimensions, and try and remove any of those dimensions if you don't believe them to be informative, and particularly try and remove them if you think that they're particularly noisy and they're likely to bring problems into your clustering problem, sorry. Measuring similarity in high dimensions can get tricky, and some weird things can happen that are kind of counterintuitive. K-means clustering won't work well for non-isotropic data, so data such as that sort of half-moon or crescent-like data. You can use the inertia or the sum squared error to choose between clusterings when the number of clusters is the same, and you can use the silhouette coefficient to choose the number of clusters that you want to use. So, what next? I'm a great believer in trying to find ways to visualize your data. As human beings, we're incredibly good at seeing patterns in data. So any way that I can find to eyeball my data in different ways, I think is hugely valuable. So this is just another way of looking at the same data that we had before. So the data is still this, I think I'm working with 2 or 3 dimensional data at this point. And what I'm showing in this graph or figure, this is basically a plot of a matrix, so a pseudo-color plot of the matrix, where the entries in each of the points of the matrix is just the sum squared error between the data points. So we've got 1,000 data points, and basically we're measuring the sum squared difference between each of the data points and each of the remaining data points. It doesn't really tell you much in this instance because there's no structure in there. but it's a starting point for a different way to look at the data. If we look at how this data looks, if we order the data according to the class labels that come out of our k-means clustering algorithm. So what we've got here is these were all the ones that were classified as being in cluster 1, and these are all the ones that were in cluster 2. Similarly, in this one, these are all the ones that were in cluster 1, and these are all the ones that are in cluster 1, cluster 2, cluster 2, cluster 3, and the same for the 4. We start to see some real structure. And what you see is a sort of block diagonal structure. And above each of these figures, I've also plotted or printed out the silhouette coefficient. So the silhouette coefficient is basically measuring the average of this block and taking a ratio compared to the blocks that are in different, or being given different class labels. And we can see it's quite obvious in this instance that the k equals 3 solution is actually the best one, because we've got nice dense regions here and very little outside. The k equals 4 one, we've got some noise or sort of poorly clustered elements here and here. And in this one, again, it's more broken up. So this way of looking at your data also gives you an intuition about the next thing I'm going to talk about, which is spectral clustering. So spectral clustering takes a representation a bit like this. It's a related representation of the data, and performs some sort of calculations on this matrix, or a related one. But it's a nice starting point for understanding what spectral clustering is actually doing. So I'll just... spectral clustering differs from k-means clustering in that it looks for connectivity between the members of a particular cluster. So whereas k-means clustering was looking for a centroid and then looking for data points that were near that centroid, spectral clustering takes a sort of different perspective, where it's looking for data elements that are actually close by to other elements, but not necessarily close by to all of the elements within their cluster. So it captures well things like that, those crescent shapes. It's also nice because it works with a similarity matrix. This means that you're not constrained to work with Euclidean distances. If you can measure the similarity between objects and create a similarity matrix, much like the, I mean, this is just a distance matrix, or the sum squared distance. But if you can create some sort of similarity matrix where each of the elements is the similarity between two data points, then you can employ spectral clustering. So it's really useful for text-based data and network data, things that don't naturally fall into a sort of Euclidean representation. I made that point. And also as a sort of something you almost get for free, it gives you a way of estimating the number of clusters that you might want to look for. So I'll start by just sort of giving you an overview of how it works, and then I'll try and unpack each of these stages to hopefully give some insight into how these set of algorithms work. So you start off, you create a similarity graph. So a similarity graph, if you understand how you can create the distance graph, distance matrix, a similarity matrix or a similarity graph is very similar. You can take a distance and apply a sort of Gaussian kernel to it to turn it into a similarity. So points that are far away are not similar, and points that are near are similar. From this similarity graph, you construct what's known as the graph Laplacian. Sorry, I sort of stepped into talking about graphs rather than matrices. I should unpack that stage. So spectral clustering comes from working graph theory, and you can represent your data in terms of each data point being a node, and then the similarity between two data points being an edge. And you weight that edge by the similarity. So you end up with a fully connected graph with each of the data points being represented by a single node and each of the edges representing the similarity. You can see a few quizzical looks in the audience. But as I said before, this notebook is available on GitHub, and if you're interested and this is hurting your head, have a look through the code at a later point, and hopefully it'll be a bit more clear. So the idea is you start with this similarity matrix or similarity graph, and from that you create what's known as the graph Laplacian. The graph Laplacian is basically you take the adjacency matrix. Sorry, it's difficult to explain this without it being complicated, and it's not. It's very simple. So the similarity matrix allows you to build the graph. I'm going to stop here. I'm going to show you the code. You construct the graph Laplacian, and it's not difficult. I'll show how it's done. From that, you then do an eigenvalue decomposition and take the smallest eigenvectors, and that provides you a new space that's much more amenable to performing something like k-means clustering. So I'm going to, sorry, that was horribly garbled. I'm going to try and unpack it a little bit. So you start with a distance matrix if we're working in a Euclidean space. We turn that into a similarity matrix by passing it through a Gaussian kernel. Then we calculate the adjacency matrix. So this is going to be a sparse version of the similarity matrix where we decide, we basically zero out some of the values to keep only those ones that are the strongest links. Now you can do that in a number of different ways. You can either say keep the links that are within the set of the k nearest neighbours. So you might say that the 10 most similar data points I will keep my connections to, and all the other ones I'll just say that it's actually a zero connection. And you can have that as a mutual k nearest neighbours. So you keep the connection only if node I is a neighbour of one of the k nearest neighbours of j, and node j is one of the k nearest neighbours of I. Or you can do it, I can't even remember what it's called. It's, so the mutual, and yeah, the first one is just called the k nearest neighbour graph, where you keep the connection if either it's one of the, because it's a, sorry. You keep the connection if node I is one of the neighbours of j, or node j is one of the neighbours of I, or the other instance, you keep it if you only keep it if both I and j are mutually neighbours of each other. So from the similarity matrix, we construct the graph Laplacian, and the graph Laplacian is formed by calculating the degree. So the degree is basically the sum of all of the weights coming into a node. So that basically the nearness to its neighbours. and the adjacency is the similarity graph with the diagonal zeroed out. We take the difference of these, and that gives you the graph Laplacian. So, as you can see, it's a very simple calculation that I've made sound incredibly difficult. It's basically these two lines. You then perform an eigenvalue decomposition on that. And if we look at the smallest eigenvalues that have come out of the eigenvalue decomposition, we can see that we have 3 very small ones, and then a step, and this would go out to 1,000. If you do the full eigenvalue decomposition on 1,000 element matrix, you would get 1,000 eigenvalues. We're just looking at the smallest ones rather than the largest ones, which is what you'd be doing if you were doing principal components or something. So it's the other end of the spectrum. So from this, we construct a new set of data, which is the number of data points by the number of clusters that we're looking for. So in this instance, we're looking for 3 clusters. So we get an 1,000 by 3 set of data. And then we can just perform k-means clustering in this new 3-dimensional space. And I'm just plotting the similarity matrix again to show the output, with the class labels being determined by the k-means clustering in this easier space to work in. So there are a number of different applications or different approaches to doing this. There's basically an unnormalized one, which is what I've just described, and then there's a normalized version. In fact, there's 2 normalized versions. And basically, the difference is in the construction of the graph Laplacian. So first normalized version is so-called symmetric version, where up until the point at which we start constructing the graph Laplacian, everything is the same. Then the difference in this instance is that we pre-multiply by the minus square root, or the inverse square root of our degree matrix, and then post-multiply by it. And there's also an extra step, which is that we have to normalize the rows of our new representation prior to performing k-means clustering in this nicer space for working in. And again, this just shows that it works. And then this third version, which is another normalized, is just a different way of normalizing the graph Laplacian. And in this instance, it's done using a generalized eigenvalue decomposition as opposed to the standard one. And we get the same sort of output. Just to show that it will work in so this is running it on the moon's data that we had before, that we could clearly see had 2 separate groups. And this is borne out by the 0 or very close to 0 eigenvalues of the eigenvalue decomposition. So in this instance, we'd have a good shout at saying that there are 2 clusters to look for. And this is the similarity matrix ordered by the output of the k-means clustering in this reduced 2-dimensional space now, because we decided there are 2 clusters. So we have just the first 2 elements of the eigenvectors. And finally, the output plotted, showing that it's able to find these 2 clusters that are well described by similarity, connectivity rather than the centroid. So just to wrap up, spectral clustering works by finding connected items. There are 3 main approaches. one unnormalized and two normalized. Just to sort of give you an insight as to why or when you might want to use unnormalized and normalized. Unnormalized spectral clustering effectively tries to balance the size of the clusters. So it's trying to, it's related to a graph cut algorithm called ratio cut, which basically takes into account the size of the clusters, the number of elements in each cluster, and tries to balance that with splitting them into separate groups. Whereas the normalized spectral clustering tries to balance the degree of each of the clusters, so how densely clustered they are. And it's approximately equal to the n-cut graph partitioning algorithm. It works nicely for non-isotropic data, provides a way to estimate the number of clusters. You can use it on other sorts of data other than just numerical or Euclidean. Anything that you can come up with a measure of similarity will be amenable to spectral clustering. And it's also deterministic up until the point that we perform k-means clustering, which is quite a nice thing. So you don't have to do multiple runs. Well, you can do multiple runs because the k-means clustering part of it will give you slightly different solutions. But if you're just trying to split the data in two, for example, you're not going to have to run it many, many times. On the negative side, you do have to create this n by n matrix and then perform an eigenvalue decomposition on it. So it can get a bit tricky when you're scaling to very large data sets. That's pretty much everything I'm going to say. So I'll thank you for listening. And